Okay, module 8 time, and again, we're covering a fair amount of material. This is a two-chapter module, chapters 11 and 12, which generally deal with the Jovian planets as well as just the debris, the leftovers from the formation of the solar system. Remember, the leading theory for the formation of the solar system is what's called the solar nebula theory, and that's the overarching theme that I want you to pay attention to as you go through these chapters and go through this lecture mixed presentation, is to see where the supporting evidence is for the solar nebula theory. Because you're going to see more of it as far as the characteristics of the Jovian planets, as well as even the characteristics of comets and asteroids and such, that these are all consistent with the solar nebula hypothesis. So that's what I want you to really focus on. Again, don't get too involved in the minutiae as far as the names of the different moons, because when you get to the Jovian planets, there's lots of moons, there's rings, and all kinds of minutiae that you would normally cover in a comparative planetology course that we're not going to focus on so much. I want you to see the big picture, the fact that the properties, characteristics of the Jovian planets are consistent with the solar nebula theory behind the formation of the solar system. Just like when we presented the terrestrial planets, here's a quick look at the relative sizes of the Jovian planets. So notice that Jupiter is indeed the biggest of the bunch, followed by Saturn. Of course, we're not including the rings in this case, just the physical size of the planet itself. And then, of course, Uranus and Neptune are much smaller. Now, obviously, these are all much, much bigger than the terrestrial planets, but comparing them, Jupiter is the biggest of the Jovian planets. And they show the Earth here just as a point of comparison. So that's one of the interesting things about the Jovian planets. Another thing that's very interesting is that none of these are surface. There is no real surface to any of these planets. What we're seeing are the atmospheres of these planets. You couldn't land on any of these planets, which is completely different than the terrestrial planets. Terrestrial meaning terra, meaning land or solid surface, terra firma. So some of the features, the characteristics that are common to all the Jovian planets is, well, first of all, they've got a lot of hydrogen in their atmospheres. Interiors are mostly liquid hydrogen. They have a lot of moons, as we're going to discover. They have rings. All of them have rings, as we're going to discover, and they also several of them exhibit what's called belt zone circulation, which we'll explain in just a moment. Okay, so of the material that was available in the early solar system, most of it went to the sun. The sun is by far the most massive object in the entire solar system, but then on its heels is Jupiter. Jupiter is the next most massive object and the most massive planet in the solar system. It contains almost 3/4 or 75% of all the planetary matter in the solar system. And what we see when we look at Jupiter is we're actually seeing cloud tops. And with Jupiter, we have these nice belts and zones. So we have these bright areas and these dark areas of cloud tops. We also have a very interesting feature here called the Great Red Spot. And so from my song, if you recall it from last module, the next thing was a blast from the past made a giant mass of gas. I couldn't write a rhyme much stupider. From Earth it looks like a dot. It's got a giant red spot and we call it the planet Jupiter. So indeed, you can see Jupiter with the naked eye. It does indeed look like a dot with the naked eye. Through a telescope, you can see a small disk, and through really good telescopes, you can actually see the giant red spot. Now, Jupiter is a massive gas. It's actually, these Jovian planets used to be called gas giants. They're more properly called perhaps gas and liquid giants, because we're going to discover that Jupiter is not all gas. It actually is made up of a funny material called liquid metallic hydrogen, which we'll explain in just a few moments. Okay, so here's a look at the interior of Jupiter, and we've already mentioned the fact that Jupiter is really, really massive. It's also really, really big. And remember, the density is mass divided by volume. So despite the large mass of Jupiter, it's actually not that dense. It's less dense than all of the terrestrial planets, and therefore it can't be made up out of solid material. It can't be made up of silicates or metals. It must be mostly hydrogen and helium, relatively low density materials. But Jupiter used to be called a gas giant, and as I mentioned, it really is more properly called a liquid giant because the pressures inside of Jupiter actually make hydrogen behave in a funny way. It forces the hydrogen atoms to get really close together and bond and form liquid. And of course, hydrogen is a metal. It's on the left side of the periodic table. It is a metallic element. And so therefore, it, in this case, will actually exhibit some of the properties of a metal. And so you've got a huge amount of metal in this planet that is rapidly rotating. And that's going to give rise to a pretty strong magnetic field, as we're going to discover. And of course, not unlike here on Earth, where we have a magnetic field, and that magnetic field interacts with the solar wind and particles from the sun to produce a aurora borealis or aurora australis, northern lights, southern lights. Same thing happens on Jupiter in a more magnificent way because the magnetic field is much, much stronger on Jupiter. As I mentioned, the Jovian planets don't really have a surface that we can observe or land on. So what we're actually observing when we look at Jupiter is we're looking at the cloud tops. And the clouds are actually made up of some interesting materials, ammonia and ammonia hydrosulfide. These are relatively massive types of molecules, and even water crystals also make up Jupiter's atmosphere. The fact that Jupiter can retain such massive gases and actually crystals is partly because of the size and mass of Jupiter and its great gravitational pull, but also the temperatures of Jupiter. You know, its location, it's so far away from the sun that it's much colder there, and that also affects the type of gases that it can retain in its atmosphere. At one time, Saturn was the only planet thought to have rings, but it turns out that all of the Jovian planets actually have rings. The big discovery occurred when Voyager 1 spacecraft in the 1970s actually ventured out past Jupiter and then turned around and looked back toward the sun and actually saw a ring. So that's part of the reason that Jupiter's ring was not discovered before then, is that Jupiter's ring is made up of mostly dust and rocky material as opposed to ices. Saturn's ring is made up of, rings are made up of ice primarily. Ice is a good backscatterer. So light leaves the sun, goes out to Saturn, hits those rings, and gets scattered back toward the sun, which of course that's why we can see those rings. Jupiter's ring, on the other hand, is made up of material that does a better job of forward scattering light than it does back scattering light. So light from the sun goes out, hits the ring material, and does not get bounced back toward the sun, and therefore we don't see it. However, when we send a spacecraft out past Jupiter and turn around, we are starting to pick up on that forward scattered light. So it turns out that not only does Jupiter have a ring, but the other two Jovian planets also have rings, but they're, again, a different composition than Saturn's ring, which is primarily ice. If you recall back in chapter 4, or module 4, we talked about Galileo discovering 4 moons of Saturn. It turns out that he discovered these 4, and they're Io, Europa, Ganymede, and Callisto. And sometimes people memorize this by saying, "I eat green caterpillars." And this is the correct order in proximity to Jupiter. So the closest one is Io, the next closest is Europa, Ganymede, and Callisto. Okay, so I don't get too fanatical about memorizing too much about these moons. Ganymede is the largest of the bunch. You can tell that it's got a solid surface, unlike its parent planet. And that's about the only significant parts of Ganymede. We'll talk about Europa and Io in slightly more detail because they're slightly more interesting. The most interesting feature about Europa is the fact that it has very few surface craters. It's a very smooth surface, and that's because it's actually an icy surface, and every time it gets bombarded by something, it cracks the ice, and then it is thought to have an ocean of liquid water below the surface, which then, of course, spills out much like magma, solidifies, and resurfaces the moon. In the last question, one of the untrue choices was that Europa was the smallest of the Galilean moons, and that's not true. Io is actually the smallest and nearest the planet Jupiter. And that's actually relatively interesting, and that actually leads into the fact that it is the most volcanic body in the entire solar system. It has 100 active volcanoes. Because of all that volcanic activity, it doesn't show much in the way of cratering. It's constantly resurfacing itself due to all the volcanic activity. Now, why is it so volcanic? It's because its innards are essentially molten, and that's because of the tidal interaction with Jupiter. It's so close to Jupiter, it's constantly being pulled, tugged internally, and all that tugging and pulling creates a lot of friction. The friction creates heat. The heat winds up creating a molten interior, and therefore a very volcanically active moon. Just to reiterate, we talked about the Jovian planets and that they formed with different building materials than the terrestrial planets. They had mostly ices to work with, little less in the way of metals and silicates and more in the way of ices. And they, especially Jupiter and Saturn, grew very, very quickly because they had kind of both. They had ices as well as they had some silicates and metals. They grew very quickly, and because of that, they reached that critical point, 15 times Earth mass, where they could actually start pulling gas that was left in the solar nebula to themselves. So that just increased their rate of growth and wound up resulting in the two largest planets in the solar system. Okay, so if you recall from the song, the lyrics go, when we reached planet 6, it all started to click and Mom was picking up the pattern. It's a sight, it wins the Pretty Planet Prize. It's a sight for sore eyes, the ring beauty known as Saturn. And certainly Saturn is the most beautiful of the planets, especially when viewed from a telescope. A lot of folks get involved in astronomy from a childhood experience of actually looking at Saturn through a telescope, because it looks like a textbook image when you look at it through a telescope with the beautiful rings. And we already talked about why the rings are so reflective, why the rings on Saturn are visible, and yet the rings on some of the other Jovian planets are not. And it's because of the material the rings are made of. The rings of Saturn are, for the most part, ice and are good backscatterers. Ice is a good backscatterer, so a lot of light is reflected from those rings back toward Earth. Now, some other little facts about Jupiter. Of course, it's Saturn, second largest planet next to Jupiter. It's much less massive than Jupiter, despite being not that much smaller, and therefore it has a very low density. In fact, its density is less than 1. The density of water is 1 gram per cubic centimeter. So therefore, if you had a big enough bathtub, Saturn would fit in it. It's a fast rotator, which actually means that instead of being a perfect sphere, it's what's called an oblate spheroid. It's again, it's for the most part a gas and liquid spinning really fast. So much like clay on a potter's wheel, the center, the equator of Saturn is a little more wide than so the distance from the center to the equator is a little longer than the distance from the center to either of the poles. So it's kind of gotten itself in the shape of an M&M. Not quite that exaggerated, but it is spinning pretty fast. And therefore it does have some pretty strong winds to go with that fast rotation. And again, just like Jupiter, Saturn has no solid surface. What we see when we look at Saturn from Earth is we're seeing atmosphere. We're really not seeing a surface. We're seeing cloud tops. And the clouds are made of, again, similar stuff to the stuff that Jupiter's clouds are made of: ammonia, water, ice, etc., etc. One of the main differences, as I just mentioned, is the fact that the winds are much stronger on Jupiter, partly because of the fast rotation. You can have winds up to about 500 meters per second near the equator. As you're going to discover, there's a lot of moons when it comes to the Jovian planets, and not all of them are that important, but one that is worth sticking in the back of your head is Titan. Titan is the largest moon of Jupiter, and is interesting enough that NASA has actually sent a probe to it. It actually landed on the surface of Titan. One thing that's very interesting about Titan is, well, first of all, it is, of course, solid, and it has a significant atmosphere, which is relatively unusual. It's not a huge body, but it is quite cold there, and it allows it to retain an atmosphere. Its atmosphere has a lot of methane in it. Methane is, and it also has a lot of nitrogen, which is interesting because Earth has a lot of nitrogen in its atmosphere, and we're always looking for other bodies out there that might be somewhat Earth-like and could perhaps support life. There is no evidence of liquid water, but there is liquid methane and ethane. In fact, oceans of ethane and methane on the surface of Titan, which is quite interesting because, of course, methane is natural gas here on Earth, and it's in a gas form here on Earth. On Titan, it's typically in a liquid form because the temperature is different there. But methane is CH4, it's carbon. And we're always interested in carbon-based life. So we know there's a great amount of carbon on Titan. So even though we think that water is necessary for life, is there the possibility that maybe there's another form of life that could get by living in methane? Who knows? So that's why it's of very great interest to NASA. But anyway, it is important to know what Titan is, if only for the lab activity you'll be doing for this module, because at the end of the lab activity in the student guide, there is a question about comparing the atmosphere of Titan to the atmosphere here on Earth. Okay, so the last little stanza in the song is, "To me and you, the last two are blue with atmospheres that cannot sustain us. In fact, they're practically twins except for how the one spins, and now you know your Neptune from Uranus." So Uranus is the seventh planet from the sun, and it's about 20 AUs away. So again, quite far away from the sun. Of the Jovian planets, now these last two are much smaller than Jupiter or Saturn. I remember Jupiter and Saturn grew very quickly and essentially hogged all the available hydrogen and helium. So there wasn't a whole lot left over for Uranus and Neptune. The hydrogen and helium that Uranus and Neptune do have is not liquid metallic hydrogen. They're just not planets that are large enough to produce the pressures required to make hydrogen behave in a liquid metallic way. So Uranus and Neptune don't have liquid metallic hydrogen. One thing that Uranus kind of distinguishes it, like I said, except that they're practically twins. They're both bluish. They're both about the same size. So they're very similar in that way, except for how the one spins. It turns out that Uranus, somewhere along the line, got knocked on its side. So its rotational axis is essentially parallel to its orbital plane. So it's kind of spinning on its side as it goes around the sun. And as I mentioned, it's far away from the sun, 20 AUs away, which means its year, the time it takes to go around the sun one time, is about 84 years. Okay, and in the lyric, of course, I said, "To me and you, the last two are blue." Uranus and Neptune have a similar composition to the atmosphere, and they appear bluish, and that's because there's so much methane in that atmosphere. Methane tends to absorb longer wavelengths. Remember Roy G. Biv, the atmosphere, so the light from the sun goes out, all the different colors. The reds tend to get absorbed by the methane, and that leaves more in the way of the blue light being reflected and heading back to us. So we see both Uranus and Neptune as taking on sort of a bluish tinge. Okay, we've already discussed the rings of Saturn that are very apparent when viewed from Earth. The ring of Jupiter was discovered only by sending Voyager out beyond Jupiter and kind of looking back toward the sun, and we saw that forward scattered material, the forward scattered light. In the case of Uranus, the ring was actually discovered, or the rings were discovered, by viewing a star, and the star's brightness appeared to change, and that was because of the rings. The rings were blocking out the light of that star and showing, creating an apparent dimming. And from that, it was deduced that Uranus did indeed have rings. Not to be outdone, of course, Neptune also has rings. It's a Jovian planet. Again, the rings of Neptune were discovered via that forward scattered light, sending a probe out beyond, turning around, seeing that indeed light was being scattered off the rings. The rings are made of, again, that darker rocky material, not ice, but more of a dark rocky material that forward scatters light more effectively than it back scatters light. As I've mentioned, Neptune is similar to Uranus. They both have a similar color. They're both about the same size. What's interesting about Neptune is that it was the first planet to be discovered calculationally or mathematically before it was actually discovered observationally. Uranus was noted that its orbit was being perturbed by something, and it had to be some other body out there. And through calculations, its position was pinpointed before, and essentially astronomers knew where to look they didn't just stumble upon Neptune accidentally. They knew exactly where to look because of the perturbation that it produced in Uranus's orbit. Neptune has many moons. Two of them are remarkable just by virtue of the fact of their orbits. Nereid, the one that's farther away, has a very elliptical, out of round type of orbit, and Triton is the only moon in the solar system that is indeed orbiting backward, is orbiting clockwise. So that's relatively interesting. Okay, so Pluto, not technically a major planet. Remember that Pluto was demoted in 2006 for several reasons. And actually, Pluto had it coming for quite a while. Pluto was discovered back in the 1930s by Clyde Tombaugh, and was tough to characterize. It didn't have, it was way out there, about 40 AUs away from the sun on average. It had a very unusual, very elliptical orbit, very out of round. So actually at some points in its orbit, it actually did get closer to the sun than Neptune. And it was known to be a rocky body. It was not a gas planet or a liquid planet. Much smaller than the Jovian planet. So it had more characteristics of being an inner planet, and yet it was located way out there. So it didn't fit in either of the two categories of inner or outer planets. It had a very, it had an orbit not only that was very elliptical, but also was out of the plane of all the other planets. It was about 17 degrees inclined with respect to the ecliptic. So that was relatively unusual. So eventually it was demoted. It was reclassified as a dwarf planet, and that's partly because there were other objects that were that started to be discovered that rivaled Pluto in size in that same part of the solar system, what's called the Kuiper Belt. And so astronomers realized they either would have to not just have 9 planets, they would have to have perhaps dozens of planets, or to go ahead and create 8 major planets and actually define what a planet needs to be, and then create a new category called dwarf planets. Pluto then became the first dwarf planet as it got recharacterized. One thing that's interesting is that the New Horizons mission, that rendezvoused with Pluto in the summer of 2015, of course is going to bring all kinds of interesting information. It carried with it the ashes of Clyde Tombaugh, who was the, again, discoverer of Pluto. He actually got a chance to go there, if not in life, but in death. Okay, so we've gotten the planets out of the way. Now we're ready to deal with the debris, the leftovers in the formation of the solar system. And in order to understand the leftovers, we need to, first of all, get some jargon under our belt. So we need to talk about meteoroids. Meteoroid is essentially any small body in space. A meteor is a small body that collides with the Earth's atmosphere but does not survive that collision. It essentially burns up in our atmosphere. That's what we see, what we call falling stars or shooting stars. When you see a flash across the sky, most likely it's just called a meteor. It probably does not survive all the way to the surface of the ground. If it does, if it actually survives the plunge and strikes the ground, it's called a meteorite. Now, most meteorites are found actually in Antarctica, believe it or not, because in Antarctica, you've got just a huge expanse of ice with no source for rocks. And if you wind up seeing a rocks out in the middle of the ice somewhere, it didn't come from a nearby mountain or something like that. It came from the sky. It actually fell from the sky. So Antarctica is a common source for meteorites. And the meteorites, as we're going to discuss, most often have a source from the asteroid belt. Not always, but most often have a source in the asteroid belt. So we'll talk about that when we get to the asteroid section. Now, small particles, as I mentioned, are what we call meteoroids. And when those small particles interact with the Earth's atmosphere, we call them meteors or shooting stars. Now, meteors, quite often they occur in what are called showers. And well, why is that? Well, how do we know? For example, the Perseid meteor shower. Every August, we have what's called the Perseid meteor shower. And that is because in August, the Earth is at a certain location in its orbit, and I'll put a little X here, and it just happens to be passing that position every August. And it just so happens that at that position, there is a trail of debris that's been left by a comet. And so essentially, every year we interact with the same debris trail. And it's that debris that now all those little meteoroids hanging out in space that now hit the Earth's atmosphere that burn up, and we see that as a meteor shower. And again, that's why we can kind of count on the Perseids being in every August, the Leonids being every November, et cetera, because the Earth encounters these debris trails at certain times of the year as it orbits the sun. Now, meteors are the ones that burn up entirely. They're usually very small to begin with, so they tend to be more in the from meteoroids, interacting with the Earth's atmosphere and burning up entirely. So meteors tend to be the remnants of comets. Meteorites tend to be a little bit objects that start out being larger and can survive the interaction with the Earth's atmosphere and get all the way to the surface. The source region for most meteorites is the asteroid belt, and the different meteorites hit the ground and can be analyzed, and quite often they have different characteristics or different compositions. Some are more rocky, some are more metallic, and that quite often has to do with the asteroid from which they came. So asteroids are quite often planetesimals that are located between Mars and Jupiter, and as they formed, they in many cases were large enough that they could actually differentiate. Remember, differentiation is when you have that settling of denser material toward the center, so your metals kind of moving toward the center, and your less dense material on the outside of a planetesimal, and those planetesimals smashed into each other and kind of broke apart, and so you would have the outer parts would be more rocky. The inner parts of these shattered planetesimals would be more metallic, and that is the reason why certain meteorites have different compositions. It's from the source region of the asteroids from which they came. Okay, so when we talk about the solar system again, it's not just the sun and the planets, it's actually anything that is gravitationally bound to the sun. And that includes the asteroid belt, and includes the Kuiper belt, which we're going to talk about, and we also include the Oort cloud. The Oort cloud are objects that are far, far away from the sun, 10,000 to 100,000 AUs away, and yet they still are gravitationally bound to the sun. And this is where a lot of comets, especially long period, comets that don't come around very often, they are thought to have their origin in the Oort cloud. As you've probably read, comets can be thought of as essentially being very low density snowballs, and they hurtle through space essentially unnoticed until they get close to the sun. And when they get closer to the sun, they start to interact with the sun. The sun actually vaporizes that ice and makes it show up in our sky. So we actually see the comet for quite often a period of weeks, if not months, as it moves relatively close to the sun, relatively close to the Earth. It turns out that when you look at a comet through a telescope, you'll actually notice two different tails. So the tail always points away from the sun, but there's actually two different tails. The one tail is essentially made up of ionized gases, charged particles that are interacting with the solar wind. And then there's also a dust tail, which is essentially dust that's set free and pushed away from the sun due to the sun's radiation pressure. So there are actually two tails that you can distinguish: the ion tail and the dust tail. Okay, so here we can see a comet as it moves closer to the sun. First of all, you'll notice that the tail becomes much more apparent the closer that the comet gets to the sun. The more vaporization occurs as those ices essentially just vaporize and become gas and dust. And so then you have two different tails. So the tail always points away from the sun. But again, the ion tail is pushed by the solar wind, whereas the dust tail essentially is being pushed by the radiation pressure. The dust tail always lags the comet, whereas the ion tail essentially points directly away from the sun. So as mentioned before, the Oort cloud is one source region for comets, and those tend to be long period comets because the Oort cloud is so far away. So those comets don't come around very often. The Kuiper belt is a closer source region for comets. This is again, Pluto is actually considered to be a Kuiper belt object. It's one of the largest of the Kuiper belt objects. It's not going to be a comet, but there are smaller objects which have more elliptical orbits that are essentially small icy bodies that will interact with the sun and are comets, and they tend to have a shorter period. And another thing that's interesting about Kuiper belt comets versus Oort cloud comets is that the Oort cloud is spherical. So Oort cloud comets can essentially come toward the sun not necessarily in the elliptical plane. They actually can come from any direction because the source region is a sphere around the sun, whereas the Kuiper belt is a source region that is essentially all these objects are orbiting on the same plane as the sun, so therefore they tend to follow the ecliptic as opposed to coming in any direction. So we discussed mostly in last module when we talked about the terrestrial planets show a lot of scarring from bombardment, and the Earth doesn't really have that much in the way of scarring, and we mentioned why, because we have plate tectonics, we got weathering, we have ways of resurfacing the Earth that the other terrestrial planets do not have. But we do get scars. In fact, here's a picture of a scar. This is the Barringer crater near Flagstaff, Arizona. Again, most of the bombardment happened early in the formation of the solar system, but there still is stuff out there, and we do occasionally get hit by this stuff. So this was 50,000 years ago, creating a fairly large crater. An even more significant impact occurred about 65 million years ago, which actually led to the extinction of the dinosaurs. A large asteroid made impact in the vicinity of the Yucatan Peninsula. Here's the Yucatan Peninsula in Mexico, and this is the Chicxulub crater. And this is again thought to have the impact is thought to have put so much debris into the atmosphere that it actually essentially created a winter, a nuclear winter, which led to the extinction of the dinosaurs as well as other species.